This lecture is about concurrent programming in Java, mostly Java memory model. Let's review the notion of processes and threads. A process is the unit of launch from the viewpoint of operating system. So every process maintains its own isolated memory space. As a result, a pointer created inside the process does not make sense at all in another process because they don't share memory space. A thread is the unit of execution within processes. So a pointer created by a thread inside the process continues to make sense in another thread running in the same process. So the other thread can safely dereference the pointer created by the earlier thread. We assume operating system threads instead of user-level threads for our discussion. Operating system threads are directly maintained by the operating system and are mapped to native threads inside the CPU cores. User-level threads are maintained by the user-level library, and when there is only one native thread available in the CPU, you can still have multiple user-level threads running in parallel. In the case of Java, every Java virtual machine creates a single process, and all the Java threads running inside the JVM are directly mapped to OS threads. The most important notion in Java memory model is happens before relation. Happens before relation is not temporal relation between statements. Rather, it specifies when the effect of executing a statement is visible to another statement that is executed later. So for example, if there is happens before relation between this write statement and this read statement, the effect of this write statement is visible to this read statement. As a result, this read statement will read the latest value assigned to variable x in this write statement. So it reads 100. If there's no synchronization between two threads, then there's no happens before relation. For example, suppose that there's no synchronization between this thread A and this thread B. Inside the thread A, we updated the variable x twice. And later, in physical time, we execute this statement in thread B. Normally, this read statement would return the latest value of 100 because it is executed later in physical time than this write statement. However, there is no happens before relationship between these two threads, so nothing can be known about the result of executing this read statement, even though it is executed later than these two statements. So it may return the original value of 99, or it may return the updated value of 100. Here's an example for demonstrating the happens before relation. We have two Boolean variables, a and b. We have two integer variables, x and y. In this first thread, we updated the variable a to true, and then we inspect the current value of a variable b to update the variable y. In the second thread, we update the variable b to true, and then inspect the current value of a variable a to update variable x. If this was a sequential program, it would be pretty easy to predict the result. But this is a concurrent program running two threads. And it's quite subtle to predict the result. In particular, it may appear that we can never have the two variables x and y set to 1 because before we update variable x and y, we execute these two statements where we set both variables a and b to true. So it seems like we can never have both variables x and y set to 1. However, it turns out that this assertion can fail depending on the scheduling of threads and interleaving of statements. Here are two scenarios that give rise to race condition. In the first scenario, we write to variable b in thread T2, and later we read the same variable b in thread T1. Similarly, we write to variable a in thread T1, and later we read the same variable a in thread T2. As a result, we see that both variables x and y are set to 0. The second scenario is similar to the first scenario, except that we read variable a in thread T2 before updating the variable a in thread T1. So as a result, we see that variable x is set to 1 and variable y is set to 0. So we see that from the same concurrent program, there can be two different outcomes, this one and this one. However, we have not taken into consideration the happens before relation, and these are not the only outcomes that we can obtain from the previous concurrent program. So for example, in the first scenario, we write to variable b here, and we read the same variable b in another thread. But there's no synchronization between this thread T1 and thread T2, and there's no happens before relation between this write statement and this read statement. As a result, there's no guarantee that this read statement will read the updated value of true. It may be that this read statement obtains the previous value of a variable b over false, in which case y is set to 1 instead of 0. So if we take into consideration the happens before relation, we can see more outcomes are produced from the same concurrent program. Now let's see the rules governing the happens before relation. The first happens before relation is about program order, which says that every action in a thread happens before every other subsequent action in the same thread. What this rule means is that a statement that appears before another statement in the same program has happens before relation with respect to the later statement, even if the compiler reorders these statements for optimization. So for example, inside the same thread, this write statement updates the variable x, and later inside the same thread we read the same variable x, and there happens before relation between this write statement and this read statement. So JVM guarantees that this read statement returns 99. The second rule governing happens before relation is about transitivity. This rule literally says if action A happens before action B and action B happens before action C, then action A automatically happens before action C. The third rule governing the happens before relation is about volatile fields. The key property of volatile fields is any write to a volatile field has immediate effect on concurrent threads by updating their thread cache. What that means is that if you write it to a volatile field, Z here, then every read statement on the same field Z will return the last value of 100. because there happens before relation between this write to volatile field and every subsequent read operation. The next rule governing the happens before relation is about locking. So this is the idiomatic use of locks. First, you acquire the lock, and then you access the resource protected by the lock within this try construct. Finally, you release the lock inside this finally construct. The reason that we restrict the access to the resource within this try construct is to make sure that the lock is released eventually inside this finally construct, even if exceptions are raised. Alternatively, you could use this synchronized construct. In this example, when we enter this synchronized block, we automatically acquire the lock associated with this foo. And when we leave this synchronized block, so for example, when an exception is raised, we automatically release the lock associated with this foo. And the rule about locking ensures that this unlock statement happens before this lock statement. So every statement executed before this unlock statement, for example, those statements executed inside this try construct, has happens before relation with all those statements executed after the next this locking operation. The last rule governing the happens before relation is about thread start and thread termination. The rule about thread start says that if a thread creates a child thread, then all these statements executed before creating the child thread happens before relation with these statements in the child thread. And the rule about thread termination says that if a thread terminates here because another thread calls join, then all these statements executed in the child thread happens before relation with those statements executed in the parent thread.